and I'm going to tell you about our work on building semantic foundations for a Rust verification tool called Verus. So let's start with what is Verus. Well, like I said, it's a verification tool for Rust that allows developers to add specifications and static checks to Rust code, like here. Like this. Thank you. All right, hope I'm good now. OK, so in Verus, these specifications are machine checked by a combination of automated theorem proving and manual proofs by the developer. Verus generally targets systems programming and supports concurrency, low-level data structures, and unsafe code, and it generally has competitive performance in the machine checking of these proofs. Verus is open source, and there is much open source code written in Verus, over 250,000 lines. Things that are verified in full or in part, such as memory allocators, OS components, and cryptographic protocols, among others. So with so much code relying on Verus, we might wonder, is Verus itself actually correct? And in fact, there's quite a lot in the trusted computing base of Verus, including Rust itself, the theorem provers that Verus relies on, Verus's own verification generation, and its trusted specifications for Rust standard library. So our goal in this project is to begin chipping away at the bottom of this iceberg with soundness proofs, though we're not going to be focused on any of these things in the slide right now. Instead, we're going to be focused on one of Verus's more unique features, which are called the proof-oriented types. So let me start by telling you what those are. To explain the proof-oriented types, I need to sort of orient you within the Rust type system in general. So within Rust, there's a spectrum of types from commonplace, easy-to-use types to harder, more unusual types. On the easier side of things, we have things like box, shared references, and mutable references, which generally enforce a fairly clean ownership discipline that makes things easy to reason about. So to be specific, I'll give you this little code snippet here. The function takes two mutable references. We assign x to 0, y to 10, and then we assert that x is still 0. Now, in Rust, these mutable references are not allowed to alias. And therefore, this assertion is always going to be true, and Verus can check it easily. This takes advantage of a property that in the Rust community is often called aliasing XOR mutable, or AXM. But as I said, these are just the commonplace, easier to use types. Within Rust, there are a bunch of harder types that make use of interior mutability, unsafety, or both. So for those who don't know, interior mutability refers to the situations where you mutate data from behind a shared reference. So by definition, these are places where AXM is violated. So how does Verus reason about these situations? Well, Verus actually has its own set of interesting types that handle these situations, which are what we call the proof-oriented types. So two of them, p-pointer and p-cell, are just proof-oriented analogs of common Rust unsafe primitives. But the other proof-oriented types are what we call ghost types, which only exist to facilitate proofs, and they have no runtime impact and no physical layout. And this collection of proof-oriented types can be used to verify many of the Rust libraries. So in this sense, the various proof-oriented types are kind of more primitive than the usual Rust libraries. Let me give a specific example of one of these types, the p-pointer type. So here's a line that does an allocation, and you can see it returns two things: a pointer, which is the p-pointer, that stands for permissioned pointer, though you can just think of it as a normal pointer. The important thing about this type is that it comes paired with a ghost type called the points_to, which is based on the concept of the same name from separation logic. This is a ghost type, and it allows us to reason about the value that is pointed to by the pointer. And it also acts as a permission that allows us to read or write to the pointer. So if we continue on with the example, I'm going to start by copying the pointer twice here. So we now have the two pointers that alias to pointer. And then we're going to write to pointer 1, and then we're going to write to pointer 2. So here I am wantonly violating AXM because we have two alias pointers that we're writing to both of them. However, in this example, we still have the points_to, and the points_to object is in fact uniquely owned throughout. And by doing this, we're able to ensure data race freedom, and it also allows reasoning about the value behind the pointer. The idea here is that we are still enforcing an ownership discipline, but we're doing so through this logical proof world of ghost types, not necessarily in a way that is tied to the physical layout of data. So that's a proof-oriented type in a nutshell. Verus, in fact, has a bunch of these, and these are all, in fact, based directly on separation logic concepts. I just talked about the points to, which is based on the classic points to of separation logic. But Verus also has types that are based on more modern separation logics, especially the iris separation logic, and one type based on a more recent separation logic library called Leaf, which is itself implemented in iris. Okay, so these proof-oriented types don't come out of nowhere. They're all related to foundational separation logic concepts. But the incarnations of these types in Verus is still only informally related to these foundational concepts. So that's what we want to try to fix in VerusBelt. We want to try to actually formalize the essence of these proof-oriented types and the relationship to the Rust type system. So that brings us to our contributions in VerusBelt. What we do is we prove a soundness theorem for a model language lambda Verus that incorporates specifications for these proof-oriented types and has a Rust-like semantics and borrow-based type system that captures the central Rust features. And it's all mechanized in Rock. Just to clarify what we're not doing, we're not going to be verifying the Verus implementation itself or any of its dependencies. We're not going to verify 100% of Verus's axioms and assumptions or use a 100% faithful model of Rust semantics or type system. So we're especially just going to get the essence of the proof-oriented types and Rust type system. So to explain how we do this, let's start with some background on Rust verification. So let's start with VerusBelt from 2018, one of the seminal works in the Rust verification space, which defines a model language called lambda Rust with a borrow-based type system. And it proves a type soundness theorem in Rock using the iris separation logic, which essentially says that a well-typed program does not go wrong. That's great, but unfortunately it doesn't work for us because the various proof-oriented types don't actually obey this property. So proof-oriented types, in order to be correct, require not only the normal Rust type checking, but they also require the checking of verification conditions. For example, in our snippet earlier, Verus has to check that all the points to objects align with the pointers that they're being used with. So unfortunately, this property doesn't hold. However, a subsequent result, the Rust Hornbelt work, builds on VerusBelt by augmenting typing judgments with specifications. And they prove what's called a type spec soundness theorem, which says that a well-typed program with a checked specification does not go wrong. And this is the sort of thing we need to do VerusBelt. So with Rust Hornbelt, we basically have a roadmap. Translate Verus types into Rust Hornbelt style specifications, and then prove this type spec soundness theorem. And so that is basically what we do. And for the rest of the talk, I'm going to talk about two of the big challenges we have to overcome in order to do this. So there's two main ones. The first one is that the proof-oriented types of Verus have many complex interactions with shared borrows whose handling in VerusBelt is somewhat non-trivial. And secondly, Rust Hornbelt has a fairly sophisticated handling of mutable borrows, which then has non-trivial interactions with the proof-oriented types. So I'll talk about both of these, starting with the first one, shared borrows. So types in Rust exhibit a wide spectrum of behaviors when they're taken behind a shared reference. So again, I'm going to contextualize this within Rust before talking about Verus. So for example, if you take a shared reference to a box, this will always give you a shared reference to the underlying data. But if you have a shared reference to a mutex, this could give you a mutable reference to the data if you were to take the lock. And if you have a shared reference to an RW lock, you could get either one. And this is just a few of them. So to handle this, what VerusBelt does is it defines a unique sharing predicate for every type. And here are a few from the VerusBelt paper. You don't have to read these in detail. I'll give you the high-level points, which are these. The sharing predicates are all propositions in the iris separation logic, which allows the VerusBelt soundness proofs to be carried out in iris. The second thing is that to write these propositions, VerusBelt developed a number of novel mechanisms known as the lifetime logic. So for each type, you will have to sort of pick and choose from these mechanisms to write these sharing predicates. But again, Verus works differently, because in Verus, these kinds of types can be derived and proved sound by combining the proof-oriented types. So again, it's the proof-oriented types which are considered primitive for the purposes of this work. And the issue then is that since these proof-oriented types sort of capture all the complex sharing behaviors that the Rust library types do, we need a sort of more systematic, uniform approach to constructing these sharing predicates of all these proof-oriented types than the sort of ad hoc per type approach used by VerusBelt. So the idea here is that we're going to create a new version of VerusBelt's lifetime logic that has one unifying mechanism for shared borrows. And to do this, we're going to leverage something called the leaf separation logic, which I actually mentioned earlier, which provides a uniform framework for reasoning about shared read-only resources via what it calls a guarding operator. We rebuild the lifetime logic on top of this guarding operator, yielding our new leaf lifetime logic. Specifically, we represent all borrows by this particular expression here, where the funny arrow in the center is the leaf guarding operator. And it very loosely means that the left-hand side resource can be used as a kind of proxy for using the resource on the right-hand side in a read-only fashion. In this case, the left-hand side resource is what we call a lifetime token, which is part of the lifetime logic, and it indicates that the borrow named by alpha has not expired. And the proposition on the right-hand side, P, is just an arbitrary proposition. So this allows us to use P as long as the borrow alpha is alive in a read-only fashion. And from this definition, we can in fact actually derive all the complex properties of shared borrows that we need to in VerusBelt. OK, so that's at a very high level the first challenge. Now I'll talk about the second challenge, which again is mutable borrows. So, right. So the challenge here is that Rust Hornbelt supports something called the Rust Horn encoding for mutable borrows, which has also been used by other Rust verification tools like Crusoe. And Verus very recently adopted this encoding within the last couple of months. But when we started the VerusBelt project, we knew that Verus wanted to adopt the Rust Horn encoding, so we knew that we wanted to incorporate it into VerusBelt from the beginning. OK, what exactly is the Rust Horn encoding? So it is an approach to mutable borrows that involves prophecy variables. Specifically, a mutable borrow is encoded as a pair that includes both the current value being pointed to by the borrow and the prophesied future value upon expiration of the borrow. So the challenge with this is not mutable borrows per se, but the prophecy variables, because the prophecy variables can cause cyclic dependencies when used in conjunction with the ghost data. So there's a paradox here, for example, where we have a prophecy going in a circle where we're prophesying the future value of some ghost state, but the ghost state itself sort of captures the prophecy variable. And this quickly leads to a contradiction because you can define the prophecy variable in a way in terms of itself. And so this is a clear unsoundness. So to deal with this, we have, in order to properly specify these interactions, we need to update the encoding of Rust Hornbelt to properly distinguish non-prophetic data from prophetic data. And if we update the coding to make this distinction, then we can actually properly specify everything in a way that sort of enforces that there are no cycles, and then we can recover soundness and prove our theorem. So with these challenges out of the way, we can complete the goals of VerusBelt, which I'll remind you of now. So the main one is that we want to prove a soundness theorem for some language lambda Verus. In our case, our lambda Verus is just based on VerusBelt's lambda Rust. And our theorem is based on Hornbelt's type spec soundness theorem, using the appropriate modifications to the methodology as I've just described. So VerusBelt incorporates specs for these proof-oriented types. And it has Rust-like semantics, of course, because it's building off of lambda Rust. And again, it's all mechanized in Rock using Iris. There's a bit more in the paper. So one challenge is the handling of cells and interior mutability, which, so you can read all about that. That turns out to be fairly tricky. We also identified one soundness issue, actually, in the specification of one of these proof-oriented types called local invariant. And we also were able to come up with a mechanism for fixing that soundness issue and prove our fixed sound. And finally, of course, in the paper you can read about the nuanced differences between Verus and VerusBelt and limitations of that nature. And that's all I have for you today, so thank you.
Thanks a lot for the talk. Who has a question? Otherwise, I can also open the questions. So I was wondering, since you now seem to have like a new lifetime logic version 2.0, basically based on Leaf, would it make do you think it would be possible to kind of redo original RustBelt based on that without involving any of these proof-oriented types, kind of directly going for the Rust type soundness proof? And would that simplify things, or would it just move things around?
I'm not entirely sure. I think in some sense it might move things around. There are a couple limitations where things that are easy in RustBelt become hard, like the definition of sin and sync in VerusBelt, or particularly sinned, is much more complicated than it is in RustBelt due to the presence of local invariant. So that might be difficult. So I'm not entirely sure. I think maybe there might need to be a little more synthesis between the VerusBelt way of doing things and the RustBelt way of doing things before it's really we'll be ready to like redo the classical RustBelt.
All right.
Hi, thanks for your talk. Could you help me understand what Rust Hornbelt is? Is it a programming language? Is it a language that's known to be sound, and you're interpreting every Verus program as a well-formed Rust Hornbelt program, or is that understanding incorrect?
So Rust Hornbelt is a framework for proving the correctness of Rust verification tools, which is why we're using it for VerusBelt, because that's our goal, is to prove. So Rust Hornbelt, it's basically the main goal of RustBelt, like I said, was to prove the soundness of Rust type system, and the main goal of Rust Hornbelt was to be a framework to prove the soundness of Rust programs that have specifications. And Rust Hornbelt is built on the same Lambda Rust programming language as RustBelt. Does that answer your question?
The questions, there we go.
Nice talk. I think one contribution you mentioned that you somehow formally define some like invariant things in the Verus. I've noticed that you prove all the things in Iris, and Iris has its own resource algebra. Do you during the paper find any difference that the Verus cannot express, but we can do that in Iris?
Let's see. So you're talking about the resource algebras in Iris versus the resource algebras in Verus. Is that your question? So there is actually there are some differences with the resource algebras in Verus, because you can take references to the ghost state, which isn't really a thing in Iris, right? So you can have like read-only versions of the ghost state, and so there are extra laws in the Verus version that correspond to like what you can do when you have a shared reference to a ghost state. So actually, in some sense, I think the Verus ones, because they have these interactions with the borrowing system, are like a little more expressive than the Iris resource algebras. And then the Verus storage protocols are like an even more expressive version of the resource algebras that do even more things with shared borrows.
I have one quick last question while the next speaker sets up. If not, well, then let's thank Travis again.